Today we're going to discuss on functions. As you know, previously I have discussed on relations, and the special types of relations will be a point of discussion for today's session. A function is a relation in which each element of the domain corresponds to exactly one element of the range. In relations, this can be related in different forms, but that relation to be a function, there must be a correspondence with exactly one element of the range. We will see more examples to clarify what that means. Let's see these relations. In the first relation, 5 is mapped into -2, and 3 is mapped into 5, and 3 is again mapped into 7. You see, 3 is mapped into different elements of the range. From the previous definition, every element must be mapped into exactly one element in the range. Hence, the first one is not a function, though it is a relation. But on the second relation, 2 is mapped to 4, 3 is mapped to 4, and 6 is mapped into -4. Each unique element of the domain is mapped into exactly one element in the range. Hence, the second relation is a function. Given this, a function in some books you might find it as map or mapping, as transformation, or as correspondence. If a function f is given for the ordered pairs xy in the domain, then we say x is mapped into y by f, and we denote this as x is mapped into y, or in other form, the functional value of x will be represented by y. Hence, in every ordered pair xy, element of f, x is being mapped into y by the function given f. A relation f from a into b is represented in the form of a f from a to b, or you can also represent it as a mapped into b by f, but this will be a function if and only if the following conditions are fulfilled. The first one, if f is mapped from a into b, then the domain of the function has to be a. So this is the domain, and no element of a is mapped by f to more than one element in b. If there is one element in a element of a, then f of a element of b must be unique. That is the key remark that we have to notice. The other remark is, if to the element x of a corresponds y under the function f, we represent it as f of x is equal to y. And y is called the image of x under f, and x is called the preimage of. If f of x is equal to y, x is the preimage and y is the image. Sometimes we call them x as independent and y dependent of x by f. The symbol f of x is mathematically read as f of x, but don't forget that if we have x times y, this is a multiplication. When we say fy could be a multiplication, if we represent it as f of x, this is not a multiplication. It's not f times x, but it is the functional value of x assigned by the function f. The third remark that we need to note here is, in order to show that a relation f from a into b is a function, we said f from a into b is going to be a function if the domain is a, and if the function is well-defined. By well-definedness or by single-valuedness is the characteristic. For all x in a, the functional value of f of x in b must be unique. The uniqueness condition is quite important. Let's see examples of this sort to help us elaborate whether the given function, the given relations are functions or not. If we consider the first one, f of 1 is 1, it means 1 is mapped into 1, 2 is mapped into 6, 3 is mapped into 8, and 4 is mapped into 8. We see each element of X is mapped into a unique element in Y, but the very important condition is the uniqueness of the dependent variable. An important point what we have to know here is if f from A to B is going to be a function, we say the domain of A, the domain of the function must be A. Now on this mapping, the domain of A is 1, 2, 3, 4, and we see that 1, 2, 3, 4 are mapped, hence it is a function. Likewise, if f is defined as f of 1 is 1, f of 2 is 6, and f of 3 is 15, the mapping 1, 2, and 3 is given into 1, into 6, and into 15. And we see that the unique conditions are fulfilled. But the domain of this function f is not A. 4 element of A is not mapped with any. Hence, this will fail to be a function. This will be function provided that f is from A into B only when A could be 1, 2, 3, so that all elements of A are mapped by the given function. C is representing mapping 1, 2, 3, and 4 into 6. All elements of A, 1, 2, 3, and 4 are mapped, and they are mapped into a unique element in the range B. Therefore, this C is a function. D is mapping 1 into 1, 2 into 6, 2 into 8, 1 into 1, 2 into 6, 2 into 8, 3 into 8, and 4 into 11. Here, you see that 2 is mapped into different elements of B. Hence, this fails to have the unique image for 2. Therefore, this is not a function. We can say this is not function and this is not function, but the remaining ones are function. At this point, you have to notice the two key ingredients of becoming a function. One, the domain has to be A. The second is every element of A must be mapped into a unique element of B. So far, we have been dealing with functions as form of ordered pairs of numbers. A function can also be described with an equation. Whenever we have y is equal to 2x plus 1, we are mapping x by a function of 2x plus 1 into y. So the value of y, which is a functional value of x, is being mapped by the relationship 2x plus 1. It is a function because for every x in the domain, 2x plus 1 is unique. Therefore, this is a function. Form of equations, we call it the linear equation. If we see f of x for ordered pairs xy related as y is equal to x squared, y is equal to x squared is a relation. It means for every x in the domain, the square of that number is in the range. If f is from A into B, where A is a domain, for every x in A, we are looking for x squared in B. And every number has a unique square of its own. Therefore, the function f from the set of real numbers to the set of real numbers represented by f of x is equal to x squared is a function. Notice that the domain is the set of all real numbers. Likewise, the range is the set of positive real numbers. Actually, this has to be positive since no negative can be square of a number. The usual ordered pair notation xy, which can be represented in the form of y as functional value of x. X is the independent one, independent variable, and y is dependent variable. This variable depends on how the mapping makes it, dependent on the functional relationship. The fourth point that we need to note is an independent variable represents a variable that is representing a number of possible values in the domain, and the dependent variable refers to the variable representing possible values in the range. We have been dealing with functions, and take note that all relations are not functions, but functions are specific or special relations with properties that the function is from A to B means the domain has to be A, and every member of the domain should be mapped into a unique element in the range. Thank you very much.